Welcome everyone. Now we are going to discuss about magnitude comparator. First of all, we will be define what is magnitude comparator. So a comparator is a special type of combinational circuit. It's primarily designed to compare the relative magnitude of two binary numbers. Okay. So the binary numbers may have n number of bits each. Okay. So it gives the output whether one number is greater than the other or less than other or equal. So the comparator will be having two inputs and three outputs. Let's see the schematic. This is a schematic representation of n-bit comparator. Here we are having two inputs A and B. Each will be having n number of bits each and three outputs. One is A greater than B and A equal to B and A less than B. If the inputs are having 1 bit each, in the sense it will be called as 1-bit comparator. If it is having 2 bits each, it will be called as 2-bit comparator. Okay. So now we will discuss about the 1-bit comparator. Generally, which is used to compare 2-bit. It consists of two inputs, as we know. Each will be having a single bit numbers. Okay. So to design a digital circuit, first of all, we have to construct a truth table of our desired output. Okay. So here, this is the truth table of 1-bit comparator. So here we are having two inputs A and B. Each will be having a single bit input and three outputs. Okay. So we are taking two cases first. First, let's assume A as 0. If A as 0, in first case, B will be 0 or 1. So in the first case, A is 0 and B is 0. In this case, A equal to B. So this output alone will be set as 1. Other two inputs are 0. In the next case, A is 0 and B is 1. So as we know, B is greater than A. So that A less than B, this output alone will be set as 1 and other two outputs are set as 0. The second case, if A is 1, we are assuming A as 1. So A is 1 and B is 0. So obviously A is greater than B. This output alone will be set as 1. Other two outputs are 0. The last case, both the inputs are 1. A equal to 1 and B is also 1. In this case, it's set as the output. A equal to B is 1. Other two outputs are 0. So this is the truth table of 1-bit magnitude comparator. With this, we will be having the formula, logic formula for every output. Okay. So for this output, which means A less than B. So A less than B equal to, we are having only one high output. So for that, the combination of input is A0 and B1. So for A less than B equal to, A less than B equal to, we will be writing here A less than B equal to, where it is A bar, which means A0 and B. A bar B. So A less than B is equal to, A less than B is equal to A bar B. Likewise, we can write the equation for A greater than B. So where the output is 1 for A greater than B, A1, B0. So A greater than B is equal to A B bar. Okay, A B bar. So for A equal to B, we will be having 1 in 2 combinations for A0 and B0 and A1, B1. So A greater than B is A equal to B is equal to A bar B bar plus A B. We will see the formula here. A greater than B is equal to A B bar. A less than B is equal to A bar B. And A equal to B is equal to A bar B bar plus AB. So with this logical formula, we will be designing a circuit with our basic gates. Okay. So this is the circuit designed with a basic gate of 1-bit magnitude comparator. Okay. So shall we explain with this one input combination? Okay. So here A take A is equal to 1 and B is equal to 0. A is equal to 1 and B is equal to 0. Okay. So if A equal to 1, this AND gate will be getting the output A is equal to 0 because here is having a NOT gate. Okay. So if A is equal to 1, if A is equal to 1 and B is equal to 0, we are assuming. Okay. So A1 in the sense here we are having a NOT gate. So the A bar will be 0 and B is 0 already here. Okay. So as this is an AND gate, for 0, 0 input, the output will be 0. Okay. Now let's see come here. In this XOR gate, A is having 1 and B is having 0. B is having 0. Okay. So B is having 0. If the output is 1, 0. It is a XNOR gate. XNOR gate will give the output when both the inputs are same. So here the output is 0. Next we come here. If A equal to 1, if A equal to 1, here the AND gate will get the input 1 here and the B is 0. So B is get inverted here when before given to this AND gate. So the B bar will be 1. So we can see here for this AND gate, both the inputs are 1. So the output of this AND gate is also 1. So here this AND gate is giving the output A greater than B. Okay. So now we got the output. For 1, A equal to 1, B equal to 0 in the sense, the output of A greater than B is 1. Okay. So in this way, the magnitude comparator works. Okay. So next we see about the 2-bit magnitude comparator. So in this, the 2-bit magnitude comparator, here is also the comparator will be having 2 inputs A and B, but both the inputs will be having 2 bits each. Okay, 2 bits each in the sense we will be having this number of combination. First, the input A is equal to A will be A0 and A1. The input B will be noted as B0 and B1. Okay. So we will construct the truth table. Let's take the first case. When input A is 0. A is 0 in the sense both A0 and A1, both the bits will be 0. Okay. So when we are writing the combination for 0, 0, A is equal to 0. Okay. So when A is equal to 0, 0 and B is also 0, 0, the output will be 1. A equal to B is equal to 1. Now, the next combination, A is 0, 0 and B is 0, 1. Okay. So, what will be the output? As we know, B is greater than A. So, the output of A less than B will be 1. We have to write here 1. So, likewise, we will see the another one combination. If A is equal to 1, 0. If A equal to 1, 0 and B is also 1, 0, both are equal. So we have to put the 1 in the A equal to B column. And other two outputs are 0. Okay. Next, if A is 1, 1, B is 0, 0. As we know, A is greater than B. So we have to write 1 in the A is equal to greater than B column. And other two column will be marked as 0. Likewise, we can write all the combination and we can write the output for all the combinations. Okay. So from this, we can write the output equations for every output. 3 outputs, we have to write the output equations. For that, we have to go for K-map. Okay. We have to go for K-map. Okay. So first, the first K-map is for the output of A greater than B. So it is a 4 variable K-map. Why it is 4 variable K-map? Because A and B, both the inputs are having 2 bits each. So 2 bits, totally 4 bits. So we are going for 4 variable K-map. In the column, I have taken B, and in the row, I have taken A. So A0, A1 and B0, B1. So we can build the K-map, and we have to put 1 where the outputs are 1. So for respective combinations, we have to write 1 and we have to group. Okay. So likewise, we have to construct the K-map for A equal to B output, and I have to construct the K-map for the output A less than B. Okay. So with this, we will be getting the equation. With the help of the logical equation, that we can construct the 2-bit magnitude comparator as this way. Okay. So this is the circuit of 2-bit magnitude comparator. This NOT gate is for complementing the input, right? So you can check the each and every combination here and you will get the output. Okay. So likewise, we can go for higher bit magnitude comparator also. In the market, we will be having the 4-bit magnitude comparators fabricated in a IC form. The IC number is 7485. Okay. So this is a 4-bit magnitude comparator. It will be having A and B input. So the 4 bits are marked as A0, A1, A2, A3. Similarly, B0, B1, B2, B3. And these 3 are outputs. Cascading inputs for this is the output, and this cascading input is given for combining two 4-bit magnitude comparator. Why? In the sense, when we compare the higher number of bits, we can cascade the ICs together. So if you want to compare 8 bits, we can cascade two 4-bit magnitude comparators. With the help of that, we can able to compare 8 bits words. Okay. So for this cascading inputs given. Here, look at here, as I told before. So we will be combining two 4 bits comparator. With the help of that, we can able to compare 8 bits. Okay. So here, look at here, A0, A1, A2, A3, and this will be taken as A4, A5, A6, A7. Like similarly, here B0, B1, B2, B3, and this will be taken as B4, B5, B6, B7. Okay. So this is for output of 8-bit magnitude comparator. These two, this is a cascading input. Okay. So let's see where the comparators are used. So comparators are used in mainly in decision making places. So on servo motor control and password verification and biometric applications and such places, so comparators are used. The one limitation of magnitude comparator is the system will be complicated when we go for higher number of bits. So that is only the limitation of this magnitude comparator. Okay. So thank you so much for patient listening. Thank you once again.